Okay, now we're going to continue on two component system. Two component system actually can be divided into ideal solution and also non-ideal solution. In ideal solution, we have two type of graph or component. Okay, one is vapor pressure composition curve. You must know this is the curve. Okay, this is the sneak peek of the curve, and then a boiling point composition curve. Okay, so this is the sneak peek of the curve. Okay, later on when we already reach that part, you can redraw this one, okay, for a bit clearer figure. All right, for non-ideal solution, which is not obey the root law, this is obey the root law. Okay, this is based on positive deviation and also negative deviation. So what are they? Let's look at. Okay, two component system is made up with mixture of two chemically independent species. Okay, just now for one component system there are homogeneous. Alright, for this one the mixture of two chemically independent species are either homogeneous in single phase or heterogeneous. Okay, in more than two phase. Alright, for example, for homogeneous two systems, for example, we have nitrogen gas and hydrogen gas, or methanol in ethanol, or alloy of copper in tin. Okay, so this is homogeneous two component. There are two component, they have different formula, but they are homogeneous to each other. For example, nitrogen gas and hydrogen gas, two different component, but they can mix together because they are gases. Methanol and ethanol, there are two different component, which is both are alcohol, but they can be homogenized. Okay, right, and then alloy of copper and tin in tin. So this is two different component, copper in tin, but then they can be homogeneous in one, in two component. Okay, all right, so heterogeneous two component system, for example, they are heterogeneous, so means that they are not mixed together, and then they produce two component system such as oil and water, clearly immiscible. Right, so we have few types for mixture components. Okay, there are three type of miscibility. One is miscible, where liquid form homogeneous mixture, for example, mix completely to form a single phase. When we add ethanol and water, for example, both consist of OH, okay, OH group, so they can mix together very well. So there are actually two components, two different formula for each, but they can form homogeneously. Alright, so they are miscible. Okay, then partially miscible. Partially miscible, they are miscible, but just half of them are miscible. Okay, we still can distinguish between the liquids. Okay, due to the meniscus, you can look at the meniscus and distinguish the phase. All right, so the volume is not identical to the original volume. All right, so partially miscible, we can see like hexanol and water, both are consist of OH, but they're not entirely miscible, not like ethanol just now. Ethanol, because of it has lower carbon number, so it can mix easily with water. But ethanol, because we have C6 now is quite complicated. Though it can mix with the water, it's not completely will be mixturous. Okay, they not completely will be mixed together. So that's why just half partially miscible. Okay, immiscible means that it cannot mix together. It's entirely not mixing around. Okay, for example, water and oil. Obviously, there are two different types of components, and there are entirely different phases. Okay, when we mix together oil and water, we completely can see the two meniscus of two different phase. All right, two different layers. Okay, now you have to know solution and root law first in order to know is it that one is ideal or non-ideal solution. Okay, a solution of homogeneous mixture made up of solute in a solvent. So we know solute, for example, like sugar. Okay, part that we mix up, okay, into the solvent. Solvent is the component that we use as the medium to mix up the solute. Okay, for example, like water. Okay, a solution made up of two liquid components may be ideal or non-ideal. The law that classifies solution as ideal or non-ideal is known as root law. Root law formula is PA is equal to XA PA naught. So notice a naught on the top. Alright, where PA is partial vapor pressure of the component A. PA naught is the pure vapor pressure of pure solution, not always refer to the pure solution of component A, and XA is mole fraction of the component A. Okay, note that because this is mole fraction, we can say 1 mole, 2 mole, 3 mole, up to 10 mole, alright? So Na, any number of mole over the N total, that will give the entire mole of the substances. Alright, so in this case, we just refer for one component or one solution, which is component A, but we can also note it as it could be PB equal to XB, PB naught, or PC is equal to XC, PC naught. Okay, it depends on what component that we are referring. Okay, so now when we are about to calculate the total pressure of the solution given by Dalton's law for two component system, Dalton said that P total is equal to PA plus PB. This is, for example, we have two component, when we have two component system. Okay, PA is equal plus PA plus PB is equal to P total. And we know from Roots law just now, PA is equal to XA PA naught. Okay, so while we take Roots law into the Dalton law, what we got, P total is equal to PA XA PA naught, okay, plus with PB we replace with XB. So XB PB naught. Okay, so this is giving us a new total pressure. Okay, this is a total pressure for the solution. Okay, so we note that X, because of X, I said earlier, is a mole fraction of component A. When we add with mole fraction of another component B, should be mole fraction plus another mole fraction should be equal to 1. So we can say that value of XA is normally around 0 point something, okay, like 0.8 plus with 0.2, for example, for XB, that will give equivalent of 1. It's always equal to 1 because mole fraction is always equal to 1 mole. Okay, right. So now we go with ideal solution. So I mentioned that two components, you have two solution. One is ideal, another one is non-ideal. Ideal solution is solution that obey Roots law. Okay, it's obey Roots law where PA is equal to XA PA naught. Okay, alright. So ideal solution are formed when the solid and solvent are similar structure. They are almost similar, okay, but they have one branch that a bit different. Okay, for example, benzene and toluene. Okay, they are actually from the family of ring. Benzene 6 ring, and then toluene also 6 ring, but now toluene, it has attachment of CH3 over it, so that's made a bit different between this one solid, one is solvent. That make them a bit different, but they are coming from the same family of C6. Okay, the actual vapor pressure of either solution normally equal of the calculated using both Root and Dalton's law, where it says P actual is equal to P calculated. So when we transform the Root's law, the ideal solution of Root's law, into the graph, what we got is graph something like this. This is a mole fraction. Look at on it. This is the mole fraction, where I said mole fraction is always equal to 1. So we may say that this is going to start with 0. Okay, at this point it's going to start with 0. So at the end point it's going to start with 1. This is if you refer the graph from left to right. But let's say if I want to refer the graph from right to left, is it wrong? No. Okay, it's still correct, but we start here from 0 on the right, but 1 on the right, on the left. Okay, so that's, it depends on who gonna be your topic and who will choose to be your where is the point of 1 and 0. Okay, so let's say here mole fraction of this is start from here to here. So now from 0 to 1. Okay, so now you have your PA start from 0, let's say from here, PA, okay, to PA naught over here, while PB start from 1 to PB naught. Okay, and then it being said that P total is equal to PA plus PB naught, correct? Okay, so that's why you got your T total. This P total, this is just like common sense how we got the total, right? Where actually it's coming from here to here, and then from here to here, then you got your P total. Okay. Alright. Okay, so now we look at that ideal solution. We got two type of graph diagram. Okay, one is known as vapor pressure composition diagram, and another one is boiling composition. Okay, so we go with vapor pressure composition. This is some slides, the example before, right? So we may say that this is XA or SB, okay, SA and SB. Okay, let's see from where we want to read it. So let's say if you read it from left to right, from 0 to 1, it says that this graph of SB. Okay, the graph mentioned like that, so we assume it's like that. Okay, but if you want to read from right to left, it's not wrong, it's also correct. Okay, but your 0 will be start here, your 1 will be here. So this is graph of XA. Okay, because I always say that XA plus XB is equal to 1. It doesn't matter from where to start as long as your final is 1. So if you start from left to right, so 0 up to 1. But if you start from right to left, same 0 from here, from right to left, 1 at the left. Okay, so it doesn't matter from where you start, but you should know who you're going to put as your start. Okay. Alright, okay, so in this case, we say that we have 0 to 1 of XB, component of mole fraction of XB. Alright, so how do we read the graph? This is mole fraction over versus vapor pressure. So vapor pressure, we can say on here, this is vapor pressure of PA naught. At the end is of B naught. Okay, why B? Because this is reach of B. How do we know it's reach of B? Because our graph is graph B just now. Because I read it from 0 to 1. So means that more is to the right, it's reach with B component. So this graph at the end is a B component. It reach more like one mole of B. Okay, at this part is 0 mole of B, or we can say that this is 1 mole of A lah. Alright, so full of A but 0 mole of A. Betul tak? Alright. Okay, so from here we can say from A to B, how do we read it? Okay, so we have two phase. One is liquid, one is vapor. Okay, so let's say from C1, let's say we mix up, we heat up the liquid, we heat up the liquid at C1. Okay, the temperature will rise. The temperature will rise, again pressure will rise, okay, to become vapor. Okay, it become more vapor until in the end it touch this line. Okay, where it become liquid vapor equilibrium. When it touch this line, when it touch this point, it cannot go beyond that point anymore because there is no phase, there is liquid phase over there, so it couldn't be more than that. Okay, so what it should do, it must return back between the curve. Between the curve, it goes this way, where it's actually the condition now is between liquid and vapor at equilibrium. It is at equilibrium. Okay, so once it's equilibrium and it touch the dotted line here, what will happen is cannot go beyond the dotted line anymore. This is the end line. So what will happen? The liquid vapor now will be start to become into vapor, where it now have more enriched of XB. Okay, so let's say the mole here is 0.4 mole of XB. So when it's heat up, it's turn more liquid, and then when it's reached this line, it cannot go beyond that far. So it goes equilibrium between liquid vapor, and then when it reaches this line, it goes down back to produce more C2. C2 here, let's say we have now 0.7 mole of XB. So by looking at this vapor pressure composition, when it started normally at lower mole fraction, when it finished it will produce more mole fraction. Okay, alright, so that's why we have improved the vapor amount of C2.